beginning of our unit on probability. Most of us have probably had some experience with probability. For example, if you ever listen to a weather report, they might give a probability of precipitation of 40%. That means that on days with similar conditions, 40 times out of 100, it rained on that day. So anyway, so this unit is going to be on probability, and also we'll get in, this week will be probability, then we'll get into random variables. In this example here, we have an example of a family during a flu epidemic. Probability of the first child getting the flu is 0.4. Let's say 40% of children get the flu. So probability of C1 is 0.4. The probability of the second child getting the flu is 0.4. The probability in a two-child family, probability they both get the flu, that's C1 and C2, is 0.25. So these are, we're going to assume that these are the conditions. So this is these are given, and then we want to use these to compute other probabilities. So just a word about notation. C1 represents the event the first child gets the flu. C1 with a bar on top, or C1 with a C, or raised C, represents the event the first child does not get the flu. C2 represents the event the second child gets the flu. C2 with a bar, or C2 with a raised C, represents the event the second child does not get the flu. These are called complements. This is the C2 bar is the complement of C2. C1, this is the intersection symbol here. You can think of it as and. C1 and C2, also written C1, C2 without any symbol in between, represents the event that child 1 and child 2 both get the flu. This symbol here is a union symbol. You can think of it as or. C1 union C2 represents the event that the first child gets the flu, or the second child gets the flu, or both get the flu. And then C1 with this slash vertical line in between, C2's vertical line C1, is called a conditional event, and that represents the event that the second child gets the flu if, or given that, the first child gets the flu. And there's some formulas. I don't like to emphasize these formulas, but for those that like formulas, the probability of C1 bar is 1 minus the probability of C1. So in other words, the probability of first child does not get the flu is 1 minus the probability that the first child gets the flu. So in this case, it's going to be, for this particular example, this is going to be the probability that the child gets the flu is 0.4. So for this particular example, it's going to be 1 minus 0.4, which is 0.6. So if they have a 0.4 chance of getting the flu, or a 40% chance of getting the flu, that means they have a 0.6 chance, or 60% chance of not getting the flu. Also, the probability of C1 or C2, you can add the two separate probabilities and then subtract off the probability of both. So probability of C1 plus the probability of C2, and then subtract the overlap. And then the conditional probabilities, probability of C2 if C1 is going to be a probability of both divided by the probability of C1. But I'll for most of these formulas, except for the conditional probability, I'm going to use I'm going to use boxes. I usually use boxes or Venn here rather than the formula. And for the conditional probabilities, I usually use a tree for this for the conditional probabilities. I think these are, if you use boxes and trees, I think it's a little bit more intuitive than using these formulas. And these formulas just give you something to memorize without maybe really understanding what's going on. So let me get into the using the Venn diagram. So this is box or Venn. I'll start out with the Venn diagram. Okay, so we're given some probabilities. We want to find some additional probabilities. So we want to find the probability of at least one child gets the flu, or the probability of exactly one gets the flu, or the probability the first child doesn't get the flu, probability neither child gets the flu, and so forth. So one way of doing this is with a Venn diagram. So the C1 circle represents the event that the first child gets the flu. And the entire C1 circle has probability 0.4. So the crescent moon is going to be 0.4 minus 0.25 is 0.15. So the crescent moon is going to be 0.15 because the entire C1 circle has probability 0.4. Where they overlap, that's where they both get the flu. That's 0.25. So this crescent moon represents the event that the first child gets the flu, but the second child does not. And then likewise here, do 0.40 minus 0.25 on this side. We also get the other crescent moon is 0.15. That represents the event that the second child gets the flu and the first child does not. And then the part that's outside either circle would be the event that neither child gets the flu. So if we so the entire rectangle should have probability 1. So if we do 1 minus 0.15 minus 0.25 minus 0.15, we get what's left over, which is 0.45. So that's going to be the probability that neither one gets the flu. And then we can answer the questions here. So for part A, let me get a different piece of paper. For part A, we want the probability of at least 1. A, probability at least one gets the flu. So probability of at least one. So that's child 1 or child 2 or both. So it's going to add up these three numbers here. So it's going to be 0.15 plus 0.25 plus 0.15. And that's equal to 0.55. And part B is the probability of part B is probability exactly one gets the flu. So that's going to be the two crescent moons. So it's going to be the first child gets the flu and the second child doesn't. That's a 0.15. Or the second child gets the flu and the first child doesn't. So it's going to be probability exactly one get the flu. See if I have a better pen here. It's going to be 0.15 plus 0.15, which is 0.3. And then C, probably first child doesn't get the flu. So that's everything outside the first child doesn't. So that's everything outside the C1 circle. So that's 0.15 plus 0.45 is everything outside the C1 circle. 0.15 plus 0.45, 0.6. Part D, probability neither child gets the flu. Well, that's outside either circle here. That's the part that's not in any circle. That's the 0.45. And then part E is the conditional probability. We want the probability that first child gets the flu if C1 gets the flu. So that's the probability that they both get the flu divided by the probability the first child gets the flu. So for that, we don't really need the Venn diagram. The Venn diagram is it's good for the so-called addition formulas, but it's not good for the multiplication formulas or the division formulas. But we can use the formula here for the conditional probability of C2 if C1, probability of both divided by the probability of C1. So so that's going to be probability that they both get it. That was given to be 0.25. And the probability the first child getting flu was given to be 0.4. 0.4 divided into 0.25. Move off with the decimal. 6 times 4 is 24. Be 0.625. So the conditional probability. So that kind of makes sense. If we don't initially each child has a 40% chance of getting the flu. But if their siblings get the flu, then all of a sudden their chances of getting it go up to over 60%. So so that makes sense because flu is contagious, right? One would expect that if somebody in your household gets the flu, then your chances of getting the flu would increase. So we say that that tells us that because the conditional probability of 0.6 something is different from the original probability of 0.4, we say that the first child's getting the flu is not independent or is dependent on whether the second child gets the flu, and vice versa. Whether the second child gets the flu is dependent on whether the first child gets the flu. So these are dependent events. An example of an independent event would be, or independent events would be a flipping of a coin. If you flip a coin and it turns up heads, the second time you flip the coin, if the coin is evenly weighted, the second time you flip the coin, it still has a 50% chance of having heads and a 50% chance of being tails. The second toss is not going to be affected by the first toss. So those would be independent events. But for flu, since flu is contagious, what happens to the first child can have an effect on what happens to the second child. So those are not independent events. But mathematically, what tells us they're not independent events is that the conditional probability of 0.6 something is different from the original probability of 0.4. Okay, so that's the Venn diagram. Now, there's another method of answering these questions. I like to call it the box method. it shows a little bit more detail than the Venn diagram. The Venn diagram has been around for several hundred years. It's kind of a traditional way of doing things. The reason I like the box method is that it shows a little bit more detail. I'll say more about that later. But when you're filling out the box, you want to first start with what's known. What's known is the probability of both, and also each individual child probability. So anyway, before I get into that though, let's first things first. I'm making the first row the child 1 row. Okay, so the row total for child 1 should be 0.4 because the child 1 has a 0.4 chance of getting the flu. The second row is represents the event the first child does not get the flu. The grand total should be 1. And we'll fill in this later. The grand total should be 1. The first column represents the effect that the event that the second child gets the flu. That total should be 0.4. The second column represents the event the second child does not get the flu, and we'll fill that in later. So this box here, this upper left box here, is in the C1 row and the C2 column. So that represents the event that both children get the flu. So that would be probability of C1 and C2. So that probability is given. So this probability is given here. This one's given, and this one's given. The rest we can compute. And we compute that basically by subtracting. So this column total should be 0.4, and in order to get the number to fill into this box here, we have to subtract. 0.4 minus 0.25 is 0.15. We get it by subtracting. Likewise, this column here is total is 0.4. 0.4 minus 0.25 is 0.15. So we can fill that in by subtracting. This row total we can also fill in by subtracting. The grand total is 1. 1 minus 0.4 is 0.6. So the C1 bar row total should be 0.6. And likewise, the C2 bar column total should be 0.6. And then we can subtract here. 0.6 minus 0.15 is 0.45. So that gives us all the things inside. So this box here, I label that C1, C2. That's in the C1 row and the C2 column. That represent the event that they both get the flu. This number here represents the event that the first child gets the flu and the second child doesn't. It's the C1 row, the C2 bar column. This box represents the event that the first child doesn't get the flu and the second child does. That's the C1 bar row, the C2 column, and this one represents the event they both get the flu. The 4 possible outcomes are they both get the flu. First child gets the flu, second one doesn't. First child gets the flu, second child does. First child doesn't get the flu, second child does, or neither get the flu. So those 4 possible outcomes are sometimes referred to as a sample space. So some of the problems may refer to the sample space, and if they refer to the sample space, that's what they're talking about, the set of all possible basic outcomes without combining different outcomes. Okay, so that gives us some. It gives us. I find it a little bit more explicit than the Venn diagram, because the Venn diagram it's a little bit awkward to put in the row totals here. We have all the inside parts of the box are included on the Venn diagram, but it gets a little bit awkward to start putting in row totals and column totals. So I like the box. To me, just the way that the box is organized I like it better. It shows the row totals and column totals, and then on the inside you have the inside totals. Okay, so then we can answer these same questions that we did with the using the Venn diagram. The probability at least one gets the flu. Well, we want to add up all the boxes where at least one of the letters does not have a bar on it. So these three boxes we have here, C, neither one has a bar here. Here C1 does not have a bar, C2 does not have a bar. So those are the three where at least one get the flu. So you add up those four. So there's going to be 0.25 plus 0.15 plus 0.15. It's 0.55. We're exactly one. That's the one has a bar, one does not have a bar. So it's C1 bar, C2. First child does not get the flu, second child does. Or C1, C2 bar, first child gets the flu, second one doesn't. So we want to add up the 0.15 plus the 0.15. Which is 0.3. Probability the first child does not get the flu. Well, we could add up these two boxes here. These are both in the C1 bar row, or just we write down the total for that for the C1 bar row. We can write down that total of 0.6. Probability the first child does not get the flu. Probability neither child gets the flu. That would be the 0.45. And then the conditional probability is going to be the same we had before. Probability of both, and we don't really need the box for this. Divided by the, this is just the formula for the conditional probability. Probability of C2 if C1, probability of second child gets flu if the first child gets the flu. The probability of both, they both get it, divided by the probability the first child gets it. So 0.25 divided by 0.4, 0.625. So that part is the same. And again, this 0.6 is different from the original probability of 0.4. These are not independent events. Okay, and that concludes this presentation.